Hi everybody, welcome to Lecture 3 of Electrical Engineering 331. In today's lecture, we will look at the rectangular function and also consider a little more about periodic functions. Some of the material that we'll be covering here is from section 1-4, and you should actually go ahead and read all of chapter 1. Okay, so what I'm going to do today is look at a few of the problems at the end of chapter 1 and help you understand how to do problems like those. So the first one is problem 122E, where you are asked to plot x5 of t, where x5 of t is equal to 5 times the rectangular function of t minus 1 over 2 minus 5 times the rectangular function of t minus 3 over 2. Obviously, to do this problem, you need to know what the rectangular function is, and this is one we have not talked about yet in class. So let's take a moment to look at that. The rectangular function of t is defined in this way. It's equal to 1 if the magnitude of t is less than 1/2, and it's equal to 0 if the magnitude of t is greater than 1/2. So here is a picture of that function, and you can see why it's called a rectangular function, because indeed it is a rectangle. And notice that the area under the rectangle is 1 because the width is equal to 1 and the height is equal to 1. And also the center is at t equals 0. This horizontal axis is the t-axis. Okay, now that's not going to be quite good enough for us to do this problem, because we need to know what happens when we shift and scale this. But fortunately, we have learned techniques for answering that question. So what I will do, both of these parts of x5 of t have the form of our rectangular function of t minus capital T over 2. So let's look and see what that would look like. Okay. Well, we're going to use the same trick that we used in our previous lecture. Since we have replaced this t by t minus capital T over 2, we will do the same thing on the right-hand side. So we bring down the 1 and bring down the 0, but this t becomes t minus capital T over 2, and likewise this t becomes t minus capital T over 2. And then we go to work. Well, the 2 in the bottom is a positive number, and the absolute number, absolute power of, absolute value. Absolute value of any positive number is itself, so we can pull that 1/2 out in both of these expressions, and we're left with this. And then we can multiply both sides of the inequality by 2. And remember, when we multiply an inequality by a positive number on both sides, it does not change the sense of the inequality. So when we multiply both sides by 2, we will come down and get this. Now, here at this point, we need to think for a moment about exactly what this means. Remember that the absolute value of the difference between two numbers is just the distance between them on the number line. So this is saying that the distance between little t and capital T is less than 1. And this is saying that the distance between little t and capital T is greater than 1. Well, if the distance between little t and capital T is less than 1, what that means is that little t is somewhere between t minus 1 and t plus 1. And on the other hand, if the distance between little t and big T is greater than 1, then either little t is less than t minus 1 or it is greater than t plus 1. And on the left-hand side, of course, we just bring down this rect of t minus capital T over 2. So this is an expression for the rectangular function with argument little t minus capital T over 2. And we can see by looking at this definition here, or actually I guess I should say actually at this equation that we have derived rather than calling it a definition, but we see from this equation, okay, it's equal to 1 when little t is between t minus 1 and t plus 1, and again the horizontal axis here is little t, and it's equal to 0 if little t is either less than capital T minus 1, which would be over here, or if little t is greater than t plus 1, which would be over here. And just for the sake of completeness here, let me go ahead, as I say, I want to label that horizontal axis is the t-axis, and likewise up here the horizontal axis was the t-axis. Let me go ahead and do that on all these graphs. Okay, we did it on that one, but we should, you should on your graphs, you should label the axes so that anybody who's looking at it will know what's going on. So I think now okay, let's see, we'll label the vertical axis. I mean, sometimes we get a little more casual, and as long as your audience definitely knows what you're talking about, it's usually okay. But if you're going to be careful, you really ought to label all the axes. Okay, so now we've taken care of all of them. Okay, so let's go back now to this problem. So we see that this rectangular function with the argument of little t minus capital T over 2, it looks like this. And what we notice is that, as was the case with the first rectangular function, the height is still 1. So changing the argument has not changed the height, but it has changed the width. When we put this 2 down here in the denominator, it increased the width. Remember that in our function up here, the width, as we have right here, the width is equal to 1, but now that we have changed this denominator here to 2, now the width is equal to 2, and furthermore, the center is no longer at 0, as was the case before, but because we are subtracting this capital T here in the numerator, the center is now at capital T. And so we can generalize this and say that the rectangular function with argument little t minus capital T over A has a height of 1, a width of A, and it is centered at T, capital T. So now that we have determined that, we are ready to do this problem. Remember that in this problem, we were asked to plot 5 times the rectangular function of little t minus 1 over 2 minus 5 times the rectangular function of little t minus 3 over 2. And that will look like this. The first part here, this first part, the positive part, is 5 times the rectangular function of t minus 1 over 2. You can see that it's centered at 1, and it has a width of 2 because of the 2 in the denominator, and it has a height of 5 here because we are multiplying it. We're multiplying the rectangular function by 5. And then the rest of the curve here, over here, is equal to minus 5 times the rectangular function of t minus 3 over 2. Again, because of the denominator, the 2 in the denominator, this has a width of 2. Because of the 3 in the numerator, it is centered about 3. And because of the minus 5 out front, this comes down here to minus 5. And everywhere else, this graph is equal to 0 because both of these rectangular functions are equal to 0 everywhere except in the region. For the first one, it's equal to 0 everywhere except between 0 and 2, and for the second one, it's equal to 0 everywhere except between 2 and 4. So this is the answer to this problem. This is what this graph looks like. So now let's move on to another problem. This one is a modified version of problem 123E in your book. It says express x5 of t in terms of the step function and the rectangular function where the graph of x5 of t is like this. Okay, so here we have x5 of t. You can see it's equal to 0 for t less than 0, and it's equal to 0 for t greater than 4. But between 0 and 4 is given as follows. It's equal to 2 between 0 and 1. It's equal to 6 between 1 and 3. And then it's equal to 2 between 3 and 4. And so we want to use the unit step function and also the rectangular function to express this function. Okay, well, I think that you all will agree that we can express x5 of t in terms of the unit step function pretty easily, and it looks like this. We jump up at t equals 0 by an amount 2, and it's going to be flat after that, so that represents 2u of t. Then at t equals 1, we jump up again, but it's still flat after that. So that increase is, we've increased by 4, and so we can reproduce that in terms of the equation by adding in 4u of t minus 1. The t minus 1 here because this starts at 1. Now it continues that way until we get to t equals 3. And at t equals 3, we go down by 4. So we have minus 4u of t minus 3. And then it continues that way until 4, and we finally, to go down these final 2 units, we say minus 2u of t minus 4. So that's how we would express this function in terms of unit step functions. And I think that that's pretty straightforward. But now we want to see if we can express this function in terms of these this new function that we've talked about, the rectangular function. And so I'd like to challenge you to turn off the video for just a moment and to try to figure out how you could express this function x5 of t in terms of the rectangular function. And let me warn you that, or maybe I should say I'll challenge you and say that there are a couple of interesting ways to do this. I mean, I think there's one way that's sort of obvious, but then there's another way that's a little bit less obvious. So as you're thinking about this, try to think of both ways to do this, and then when you think you have it, come back and resume the video. Okay, so I hope that you were able to find at least one way of expressing this function in terms of rectangular functions, and even better, if you were really creative, I hope you could find 2 ways to do that. But let's see how this goes. Well, to me, the easier way, the more obvious way to express this function in terms of rectangular functions is to think of this graph up here as being 3 rectangles. You have one rectangle from 0 to 1, you have another rectangle from 1 to 3, and you have another rectangle from 3 to 4. Okay, so let's look at it that way. Now this rectangle from 0 to 1, it has width of 1. It is centered about 1/2, and it has a height of 2. So that would be 2 times the rectangular function of t minus 1/2. The denominator here below t minus 1/2 is just 1, because this has a width of 1, so we don't have to change anything about the denominator. The height, or the function, is multiplied by 2 because the height is 2, and we have written this as t minus 1/2 because it's centered about 1/2. Now likewise, if we go ahead and jump over to this last part, because it also has a width of 1, and so there we have 2 times the rectangular function of t minus 7/2. 7/2 because 7/2 is 3.5, and once again multiplied by 2 because the height is 2. So I think that that's clear. And then finally we have this middle portion, and because it goes up to 6, we'll multiply by 6 out here, and it's centered around 2, so we have t minus 2 in the numerator. But now for the denominator, the width now it goes from 1 to 3, and so that's a width of 2, so we have to divide by 2 now to get that width of 2. So here is one way to write this function in terms of rectangular function. But let me show you now another way that I hope you saw, but maybe you didn't, because I'll admit that it's certainly easy to overlook it. But another way to regard this function is to regard it as 2 rectangles. Now you say, well, where's 2? Well, you have this long rectangle here along the bottom, and another one stacked on top of it right here. So if you didn't see that way of looking at it, stop the video now and think about it that way, and try to write an expression for the function in terms of rectangular functions when you look at it in that way. Again, we have a long rectangle down here from 0 to 4 and with height 2, and then we have another rectangle up here stacked on top of it, centered about 2. So see if you can write that and then come back to the video. Of course, if you've already done it, then just continue watching the video. Okay, so when we view the function in this second way, this is what we're going to get. The long rectangle here at the bottom has a height of 2, so we're going to multiply by 2. Furthermore, this long rectangle at the bottom is centered about 2, so we have t minus 2 in the numerator. And finally, this long rectangle has a width of 4, so we have 4 in the denominator. Now, what about the rectangle that's stacked on top of it? Well, that one is centered about 2 as well, so we still have t minus 2 in the top. But the rectangle that's stacked on top only has a width of 2 rather than 4. So the denominator down here will be 2. And then finally, be careful about what you multiply by. This we're only looking at the part that's stacked on top of this rectangle. So that part is just, it has a height of 4. We've already taken care of the bottom portion here, because remember, we included this whole rectangle, so we only need 4 more up here. So we would multiply this by 4. So I think that that's an interesting problem to see those two different ways of writing x5 of t in terms of rectangular functions. And of course, again, here it was written in terms of the unit step function. So writing it in terms of the unit step function took a little more writing than did writing it in terms of the rectangular functions. There were, but I guess instead of saying a little more writing, I should say there were more terms. Here there was 1, 2, 3, 4 terms when we wrote it in terms of the unit step function. If we write it in terms of the rectangular function, this way required 3 terms, and this way required only 2 terms. Okay? And now the last question that we will look at for this lecture, we're going to change gears here. In a previous lecture, we talked about periodic functions, but we didn't do much with it, and so I wanted to consider a problem where we look at a periodic function, and this is going to be actually a little bit of a challenging problem, so watch carefully. This is problem 130A in your book, and it says determine the period of x1 of t where x1 of t is equal to 6 cosine of 2 pi over 3t plus 7 cosine of pi over 2t. Okay, now we know that the cosine is a periodic function, but let's remind ourselves of what the period of the cosine function is. Okay, so we're going to look at the period of the cosine of at plus theta. Okay, now we remember from earlier, whenever you studied trig functions, that when the argument of the trig function increases by 2 pi, the function will have the same value. It will repeat. And so, and of course, the only way that the argument can increase, I mean, a is taken here to be a constant, and theta is a constant. The only thing that's varying is t. So when t increases by a certain amount, that will make the entire argument increase by 2 pi, then the function will repeat. And so we need to figure out that amount by which little t needs to increase to make that happen. Okay, so again, to make cosine of at plus theta repeat, increase the argument by a multiple of 2 pi. So, well, what is the increase? How much do we increase the argument? Well, if we change little t from little t to little t plus capital T, then our new value of the argument will be this. It'll be a times little t plus capital T plus theta. Our original value of the argument is this, is a times little t plus theta. So the increase, this, what we have on the left here, that represents the increase in the argument. Again, this is the original value of the argument, at plus theta. And then as we change little t by an amount capital T, the new value of the argument will be a times little t plus capital T plus theta. And so if we take the new argument minus the original argument, that gives us the increase in the argument. And we want that increase in the argument to be some multiple of 2 pi in order for the cosine to repeat. Okay. Now let's go ahead and multiply out these things and do this subtraction. So a times little t plus a times capital T plus theta minus a times little t minus theta is equal to n2 pi. Well, you see that the a times little t and the minus a times little t goes away, and theta minus theta goes away. So all we're left with on the left-hand side is a times capital T, and on the right-hand side we have n2 pi. And then, so we have a times capital T is n2 pi, and if we divide both sides by a, then we have capital T is equal to n2 pi over a. This expression gives you the period of the function. As long as n is a positive integer, now we're assuming here that a is positive, okay? So as long as n is a positive integer, any t that has this form will be a period. We get the fundamental period by letting n equal the smallest positive integer, which is 1. So the fundamental period t0 is given by t0 equals 2 pi over a, but as long as little n is any positive integer, then any expression like this, n2 pi over a, is a period of cosine of at plus theta. So now that we have found that out, we can say, now remember we have two different cosine terms here. And the thing that's sort of tricky here is that these two functions, notice that this is cosine of 2 pi over 3t, this is cosine of pi over 2t. So these two cosine functions do not have the same period. And we're going to have to figure out how to handle that. Okay. So according to what we've just found out up here, the period of 6 times cosine of 2 pi over 3t is n2 pi. Remember, we just take n2 pi divided by a, where a is the coefficient of t in the argument. So the period of 6 cosine of 2 pi over 3t is n2 pi divided by 2 pi over 3. And likewise, the period of 7 cosine of pi over 2t is m. I'm going to pick m as another integer here, positive integer. M2 pi divided by pi over 2. Well, when we simplify these fractions, n2 pi divided by 2 pi over 3 is the same as 3n. And again, remember, n has to be a positive integer. And m2 pi divided by pi over 2 is the same thing as 4m, where m is also a positive integer. So we want to find out the period of the overall function. Here's the overall function. And the way that we're going to tackle this is to say, well, if we can find some values such that both of these terms individually repeat, then we know that their sum will also repeat. And that's the reasoning that we're going to use. And we have found out that the first term will repeat if we increase little t by an amount 3n, where n is any positive integer. And the second term will repeat if we increase little t by 4m, where m is a positive integer. So in order to have both terms repeat, what we will do is find a number that can be written in both of these ways. We want a number that can be written as 3 times n, where n is a positive integer, and also a number that can be written as 4 times m, where m is a positive integer. Well, an obvious choice for that would be 12. Okay? And so 12 is a period for this function. And I'm claiming that this is actually the fundamental period for this function, and I cannot easily prove that. But you weren't asked to find the fundamental period. When I say determine the period, any period will do. And so I claim that 12, even though I can't prove that it's the fundamental period, we can prove that it is a period. So let's see how that would go, and then that will be the last part of this lecture. So x1 of t plus 12, remember x1 again, one final time here, x1 of t is equal to 6 cosine of 2 pi over 3t plus 7 cosine of pi over 2t. So that means that x1 of t plus 12 is 6 cosine of 2 pi over 3 times t plus 12 plus 7 cosine of pi over 2 times t plus 12. Now if we multiply both of those arguments out, we'll get 6 cosine of 2 pi over 3t, and then 2 pi over 3 times 12 would give us 8 pi. And the second term would be 7 cosine of pi over 2 times t, and then pi over 2 times 12 would be 6 pi. Well, notice that 8 pi is a multiple of 2 pi, so we know that this just becomes 6 cosine of 2 pi over 3t. And likewise, 6 pi is a multiple of 2 pi, so this becomes 7 cosine of pi over 2t, and the sum of these two is just x1 of t. So we have proven here that x1 of t plus 12 is equal to x1 of t, and that proves for sure that 12 is a period of x1. It doesn't prove that it's the smallest period, but it does prove that it's a period, and that's all that we were asked to do in this problem. So that shows you how to do 3 of the problems at the end of chapter 1, and I think that these are definitely good problems to understand. So that concludes lecture number 3, and good luck.